Everybody, I want to show you some ideas about how to take antiderivatives when you have sines and cosines in your integral. So you already know that the antiderivative of cosine of x dx is sine of x plus c, and the antiderivative of sine of x is negative cosine of x plus c. And we also know a couple of things about identities, and these are going to be really helpful for us. First of all, we know the Pythagorean identities. And the important one for us here is that sine squared of x plus cosine squared of x equals 1. And of course, you can use algebra on this. You can write that sine squared of x equals 1 minus cosine squared of x. Or you can write that cosine squared of x equals 1 minus sine squared x. Okay, those are pretty easy to see, but I just want to make sure that nobody overlooks those possibilities. We've also got two other ones that are going to be important for us, and that's going to be sine of 2x. That identity is 2 sine x cosine x. And then we've got another one that we're going to use quite a bit, and that is cosine of 2x. And this one has actually two forms. The basic form is cosine squared of x minus sine squared of x. But if we use these two Pythagorean identities, we can rewrite this. So another form for cosine 2x would be 2 cosine squared x minus 1. And another one would be 1 minus 2 sine squared x, just by substituting in for sine squared or cosine squared. Those are going to be really important for us. So the first type of integral we're going to look at is if you just happen to have one sine or one cosine and the rest of the integral is in terms of the other one. So if I had, for example, cosine cubed of x times sine of x dx, we know that the derivative of cosine is negative sine, and there's a negative sign right there. So this would be a really easy integral to do. I'll just let u be equal to cosine of x. And when I take the derivative, I get du equals minus sine of x times dx. And I'm going to multiply both sides of this equation by minus 1 to get negative du equals sine of x dx. And then when I substitute in here, here's my cosine x, but it's cubed, so that will become a u cubed. Okay. I also have a sine of x dx, which is right here. That'll become a negative du. And so that antiderivative will become negative u cubed du, which is very easy to integrate. It becomes negative 1/4 u to the 4th plus c. And then we substitute back to get negative 1/4 cosine to the 4th of x plus c, and that's our answer. We'll look at another one here, just a second. So now we want to look at what happens if we don't have a single sine or a single cosine. In that case, we can convert our sines and our cosines over. So maybe I might have, oops, let me get my pencil working. Come on, pencil, do your thing. So we might have something like cosine squared of x times sine cubed of x dx. In this case, we would want to try to convert this either the sines into cosines or the cosines into sines, so that we have a single sine or a single cosine left over. In this case, if I convert this cosine into sines, well, that would be a cosine squared, and so when I convert it, I don't have any cosines left over. So that's not going to help me. So instead, I'm going to convert the sine over. I'm going to think of it like this. Cosine squared of x times sine squared of x times sine of x dx. I'm reserving this sine of x so that I can use it in my du. Now I'm going to convert this into cosines. So there's my cosine squared of x, and this is 1 minus sine squared of x. Oh, excuse me, 1 minus cosine squared of x. Let me fix that. Times sine of x dx, and this becomes a cosine squared x minus cosine to the fourth of x, all times sine of x dx. And again, we can let u be equal to cosine of x, and then du will be minus sine of x dx. I'll move that negative over to the left-hand side. This side will become my du, and in the parentheses I would have u squared minus u to the fourth. And again, that's very easy to evaluate. I won't go any farther with that. We know what to do. What can get tricky, though, is if we don't have an extra sine of x or an extra cosine of x to act as our du. And this happens when we have even powers of sine or an even power of cosine. So for example, get this pen working. If I have the integral of cosine squared of x dx, I can't reserve a sine to be my du because I need both of the cosines in my cosine squared to convert over into sines. So that won't work for me. Instead, I'm going to use the double angle identities with cosine down here. Okay. Now, I've got a cosine squared of x, so in particular, I'm going to use this one. Cosine of 2x equals 2 cosine squared minus 1. I'm going to solve that equation for cosine squared of x. So cosine 2x equals 2 cosine squared x minus 1. I'm going to add 1 to each side and subtract, I'm going to add 1 to each side. Cosine 2x equals 2 cosine squared of x, and plus 1, and I'll divide both sides by 2. And this will give me cosine squared of x equals 1/2 plus 1/2 cosine 2x. And that we know how to integrate. So this integral becomes that because of identities. 1/2 minus or plus 1/2 cosine 2x dx. I can let u be 2x. du will be the derivative of 2x is 2, so 2 dx. I'll divide by 2. 1/2 du equals dx, and this integral will become 1/2 plus 1/2 cosine u times another 1/2 du, and that I know how to integrate. Becomes, let's see, 1/4 plus 1/4 cosine u plus our du, which after I integrate, let me erase a little bit up here. We've already used that. We're not going to need it again, so I'm going to get rid of it. This becomes 1/4 u plus 1/4 sine u plus c. And again, I come back and I get 1/4 times 2x plus 1/4 times sine of 2x plus c. And there's my answer for that. This is going to come up in the next couple weeks. We're going to see some things that have a cosine squared of x or a sine squared of x dx, and there's not a really good way to handle that unless we use this double angle identity, and then it becomes quite easy. Okay, that's all for now. See you in class. Thanks. Bye-bye.